Hello YouTube. In this tutorial I'm gonna give you a very simple way and short way to simulate and find the power efficiency between two coils. Let's say that you're looking at how much power you can transfer to another coil with this and this design and structure. So to do so, if you were following the previous tutorials, you can know that I left you guys off with design in Maxwell that we had two coils with basically four terminals, and we ran simulation by defining the in the materials we defined a matrix. In the matrix we had two terminals, and basically we had these two terminals for our system, and we ran all the simulation and we got some results, and we basically found out what is the coefficients between the two coils, what is the mutual inductance, and so on and so forth. But now I want to import all these important values into Simplorer, and I want to use that in order to apply some actual current, actual voltage, and I want to also put a capacitor in series to see if a magnetic resonance is going to help the power efficiency and boost it up, and things in this nature. So to do something like that, let's start from where we left off the last time, which was here. So we already have our Maxwell file. Now I'm gonna save the Maxwell file, and it will save all of our simulation results at the same time. And then I'm going to go and basically find my Simplorer design. In the Simplorer design, as you can see, if you were following the first tutorial that I had about how you can set up a transient simulation between Simplorer and Maxwell, you know how to bring all these components. Basically, these components are hidden here in the component tab, and you can have the wattmeter, resistor in voltage, and the capacitor. And what I've done here is I've basically put a capacitor here in series with the inductance that I have, and one capacitor in parallel, based on your design. But if you want to have a maximum power delivered to the TX, you want to have a resonance LC in series, so you have maximum current going through the L, instead of having that in parallel, which gives you zero current in. And also for the transmitter side, you want to have in parallel, so you have maximum voltage dropped on the resistor. And if you have it in series, then you would get all the current in between the L and the C, and you wouldn't deliver anything to the resistor or the L. So on the top here I have the value for my resistor. I put a resistor with the value RL. I can change it whenever I want. I defined RL to be I think 100 ohms. 100 ohms. I have my RX resonator or capacitor CR, and I have my TX resonator capacitor CT. I have a wattmeter and also a series resistance in order to calculation works. So what I'm going to do is I'm going to go to the Simplorer circuit, and in the subcircuit I'm going to select Maxwell component, and then I'm going to go and add a dynamic inductance. Dynamic inductance is what we've done by defining that matrix in the Maxwell. So that matrix is basically hold all the inductance information about our structures, and pass it to the Simplorer as think about as S parameters, but it's L parameters in a way. So you can think it like that. So I'm going to select that, and I'm going to give the path of my Maxwell file, or you can just simply select browse and find the file and then select it. And then I'm going to say that the design is a 3D design, and as soon as I do that, it will retrieve all the data regarding the design, and I will press OK. Okay, now you can see that the design comes with the thumbnail of the structure, and I'm gonna put it in the middle here so you can start. One thing that you have to check is, for some very weird reason, in Simplorer, and these number of the terminals are not exactly what you think. Um, so one way to check what this terminal means, what is T2, what is T1, the names are not the same as what you defined in the Maxwell, is to double click on that, and you just go ahead into the general area, and here it says the display name of T1 is actually T1, and if you follow up the T1, you will realize that the T1 is basically RX. So basically this is RX, and then T2 is supposed to be the T2 is the TX, T3 is RX again, and T4 is TX. So it's supposed to be working like this, but I have a feeling that it might be in reverse order. For some reason, there's a bug here, at least in the version that I'm using, where it says that these two are the TX and these two are the RX, but it's actually the opposite. So let's see. Let's go ahead and just find um, the efficiency when the distance is 4 millimeter. So good thing about Maxwell is because we already solved for different parameters of distance, it will keep all the results, so you don't need to go through second simulation time. So for the distance that we are looking, which is distance equal 4 millimeters, we do know that the the TX has an inductance value of 7.326 micro, and the RX has the inductance of 3.324. That's actually the coefficients. Less than 1 micro Henry, actually. It's pretty small. So what I'm going to do is I'm going to put some values for the cap, CR and TX, in a way that these two are resonating exactly at let's say 10 megahertz, 100 kilohertz, which is the same as WPC. Let me just find the value for the capacitor, and then basically the value of the capacitor is 1 over F squared divided by L. It's 1 divided by F squared times L. That's basically the value of the C. And also you have to times it by 4 pi 2, I think. No, sorry, you have to divide it by 4 pi 2 as well. I'm going to go ahead and just use one of those online calculator and come back with the results. Okay, the values I calculated, the online calculator did the calculation, and it turns out that the CT should be, actually I defined it as, I'm using one of my old Simplorer file, and I already defined that as a function of fn, but I'm not going to do that. So the value of the C is, if you find it, it should be 345.76 nanofarad. Of course, you cannot find with this exact number, but just for the sake of the simulation, just stick with these numbers. And for the CR, we will have a much larger capacitance, 2.5628, and that would be microfarad. Okay, and everything is done now. Once again, it was 25 minutes and I had to split it into two. Sorry, please watch the next video.